The last section that we're going to do are all angle questions. So what we're looking at now is rates of changes of angles. So, for example, I saw in a textbook a baseball question. When the pitcher pitches the ball is traveling at a certain speed, and as you're hoping to hit it, your eyes have to look at that ball and follow that ball as it gets close to right in front of you where you need to swing your bat and hit the ball. As it's getting closer though, your eyes have to change their angle, and as it gets really close, how fast do your eyes have to be moving in order to still trace the ball? Now, if you do the actual math behind it, your eyes have to move faster than physically possible. So you can't actually move your eyes and trace the ball at the same time because it's moving too fast. So that's why they say hitting a baseball is one of the hardest things to do, because you have to do a whole bunch. Your body has to adjust for the fact that you can't actually see it slowly moving in front of you. So that's the thing, because your eyes are changing an angle. Those are the types of questions we're going to look at now. So here we've got a TV camera positioned 4,000 feet, which is much better than 4 feet, from the base of a rocket launching pad. So we need to draw a picture. Here is the camera. Ooh, fancy, nice. Beautiful looking camera on the ground. And it is 4,000 feet away from the base of a rocket launching pad. We should start the engines up a little bit. There we go. Okay, so this rocket is going to fire up vertically and is going to be rising at a speed of 600 feet per second. Question A is, how fast is the distance from the television camera to the rocket changing at that moment? So at the moment when the rocket is up here, (3,000 feet above the ground, we're looking for how fast is the distance from the television camera to the rocket changing. So part A is a right angle triangle one like we've done before. I'm going to call this my x, this my y, and this z. And all of them except for x are functions of time. Because what do we know? Well, dx dt is 0 because it doesn't change. But dy dt, we are told, is changing. Dy dt is 600 feet per second. And we want to find dz dt. So because this one's equal to 0, we basically know that y is a function of time and z is a function of time, and we're finding out specifically, trying to find out what dz dt is at 3,000 feet. So being a right angle triangle, can you make an equation? X squared, which is going to be 4,000 squared, because it doesn't change, plus y squared equals z squared. So there's our equation. We can find the derivative with respect to t of that equation. What also do we know is we are trying to find the specific instance when this is 3,000, and that makes a nice triangle, the 3, 4, 5 triangle, so we know that that side is 5,000. So when we take our derivative with respect to time of this equation, we get 0 plus 2y dy dt equals 2z dz dt. Plug in our values, we're going to get 2 times 3,000 times 600 equals 2 times 5,000 times dz dt. And a little bit of mental math here. What do we get? I'm going to divide both sides by 1,000. I'm going to get 3,600. Divide by 2. dz dt will be 1,800 feet per second. So there's part A is a review. We've done those kind of questions with our right angle questions before. But part B, oops. What? Oh, there's part B. I went too fast? Okay. Oh, I made a little mental math error. Can you see on this side I just divided by 2, but I would still have the 5 there? 2 times 5 would be 10, and it should be 360. There we go. For part B, we can use our diagram from before. Now, as that rocket goes up, in order to keep focused on the rocket, the camera needs to be changing its angle. So this angle right here is going to be changing. And if we want to find out how fast it's changing, we are asked to find d theta dt. So that means theta is a function of time. What do we know? We know dy dt is still 600 feet per second. So we know y is a function of time, and we want to find it exactly when y is 3,000. So can you think of a way to make an equation with theta and y? And I think that's often the hardest part in these questions, is trying to figure out, okay, what do I know that relates these variables that I have? And because I want to find d theta dt and I have dy dt, I wanted to make an equation that just has thetas and y's. In this case, because it's a right angle triangle, and we want this angle theta, y would be the opposite side. We know the adjacent side, so we could make this equation that tan of theta is y over 4,000. Now it's important to note that all of our derivatives, and we didn't say this when we initially learned our derivatives, but you know how the derivative of sine is cos, and the derivative of cos is negative sine. Those only work when the angles are in radians. You would have an extra transformation to be done with degrees. And so another reason that radians is sort of the angle of choice after grade 11 is that in calculus, all of our derivatives are based on angles being in radians. So in this question, when you're doing this and you take the derivative, you're already assuming that everything is in radians. So what would we get here if we took the derivative? Well, the derivative of tan, so we take the derivative with respect to time. Derivative of tan is secant squared, and then implicit differentiations, d theta dt. Derivative of 1 over 4,000y would be 1 over 4,000 dy dt. So in order to calculate this, we need to know what secant squared is. We need to know what dy dt, which we already do. So we need to either figure out theta or figure out secant theta in order to figure out secant squared. We are finding it again at the instant where the height is 3,000. So we have to make a decision, what's easier? Is it easier to find theta? Well, actually they're both, if you have a calculator, so if this was a calculator question, how hard would it be to find theta? Theta is going to be tan inverse of opposite. All right, if I take off the zeros and just write 3/4, 3,000 over 4,000. So if we go to our calculator, make sure that our mode is in radians, and we go tan inverse of 3,000 divided by 4,000, we get that our angle in radians is 0.64344,435, ... So we can get that angle, and then we can calculate that d theta dt multiplied by secant squared is 1 over cos squared. So if I multiply both sides of this equation, dy dt was 600. If I multiply both sides by cos squared, this is what I would get. And I could type that into my calculator. 1 divided by 4,000 times 600 times cos of that answer from before squared and I get 0.96 radians per second. Now your other option in this equation, if this was a non-calculator question, and you're like, how would I do this without a calculator? Because that 0.6435 and all of that looks complicated. Well, if from here I had d theta dt equals 1 over 4,000 times 600 times cos squared of theta, can you see from your triangle that you could figure out what cos of theta was without figuring out what theta is? Cos is what over what? Adjacent over the hypotenuse. Can you see that the adjacent over hypotenuse would be 4/5? And so if I squared it, I would get d theta dt equals 600 over 4,000 times by 4/5 squared is 16 over 25. Mental math, okay, looks a little scary, but 2 zeros would cancel out there. So you have 6 over 40 times, let's do it slowly, d theta dt, 6 over 40 times by 16 over 25. Can you see that I could cancel out a 4 and the 40? So I would get something isn't quite jiving here. So that would be 6 over 10, 4, oh maybe this will work, 4 over 25. Can you see anything else? We could reduce this to 3/5. Still not, I'm not enjoying something, I think something went wrong. Anybody see a mental math error? .096? Oh, good. Like that? Okay. Because my numbers over here, we're not going to make .96 at all. But now we get d theta dt. Oh, but now I'm worried. But this looks reasonable. Is 12 over, yeah, that's what my calculator says. 12 over 125 is the same thing. Okay. I was looking for a mistake on this side, and I just wrote it wrong for my calculator on the other side. Thank you. So you could do this without your calculator and get 12 out of 25. Of course, this also still would be radians per second. So our last angle question. We'll do this one together, and then you have some time to work on the homework. Or would you like, I could give you this one to work on, because I don't think in the homework that's listed there are very many angle questions. Would you like just to have this one for your homework question, or would you like to do it together? Do it for homework? Okay, we can start tomorrow's class with this one if you have trouble with it. Okay? That way you have more time to work on these questions. On the video as well. So there's the answer. I don't know, you'll have to pause it. There's the answer to that one if you want to watch it.